Okay. Good morning, everyone. Good morning. My name is Valyappa Lakshmanan. Everyone calls me LAK. Welcome to Google Bangalore. We're going to be talking about machine learning and data analysis on the Google Cloud. Right? So first thing, of course, is to say, why on earth do we want to do data analysis on the cloud? We probably have been doing statistical analysis, data analysis on our laptops, on small machines, maybe on a server farm, right? So what is it about the cloud that makes data analysis better? So why do data analysis in the cloud? Well, one aspect of it, of course, the thing that whenever someone talks about the cloud, you think of the physical infrastructure, right? And in terms of physical infrastructure, whether it's Google, whether it's Amazon, it's Microsoft, we've all been building these very massive pieces of infrastructure. And taking Google, something like that always blows my mind when people tell me this. It's 1/5 of every CPU, right, produced in the world every year is bought by Google. So Google buys 1 in every 5 CPUs, and this is year after year after year. Okay, so you can imagine the size of this infrastructure that we're talking about. When we talk about, like, someone says we built the most powerful infrastructure, it doesn't actually hit you until you realize that we own 1/5 of every CPU in the world. Networking-wise, the amount of fiber behind the Google firewall is bigger than the rest of the internet combined. So it's incredible amount of physical infrastructure that you get to run your data analysis jobs on. So you think in terms of your data isn't big when you're talking running it on an infrastructure this powerful. So that's one aspect of it. The other aspect is, of course, that Google has invested for many years in building a big data stack and being able to process data at a very large scale. And of course, many of you have heard of MapReduce, right? The MapReduce was a paper that was written by Google Research, right? And that essentially formed the foundation of what? Of big data, of Hadoop, right? Of Pig, of Hive, all of these things came out of these ideas that came out of the MapReduce paper, right? So Duck Cutting read that paper and implemented Hadoop. Okay, so that is what it was, right? So Google File System is the basis of the Hadoop distributed file system, HDFS. MapReduce is the basis of Hadoop. And today you can go ahead and run MapReduce jobs on something called Dataproc that we'll talk about. But by 2006, so this paper got published in 2004. By 2006, Google was no longer doing any MapReduce. Right? So we had stopped doing MapReduce by the time everyone else in the world was basically getting up to speed and writing Hadoop jobs. So what replaced MapReduce at Google? What replaced MapReduce at Google is a combination of Dremel and Flume. Right? So we'll talk about what those are, but those essentially became BigQuery and Cloud Dataflow. So what we'll be talking about at the cloud platform is the things that you do after MapReduce. Right? There are going to be limitations associated with MapReduce, and we'll talk about what they are and why it is that by 2006, we had stopped using MapReduce completely within Google. And we had moved towards what in the GCP world is called BigQuery. Right? Inside Google, it was called Dremel. Right? And there's, again, all of these are published papers. Right? So Google's always been in the forefront of publishing it. So when you talk about why do data analysis in the cloud, one answer is the physical infrastructure. The other answer is that you get to use much better tools in order to analyze the data, right? Beyond something like Hadoop, beyond something like Spark. So we'll talk about what they are and what the limitations are and why we want to do it that way. So that's basically what we call the big data stack version 2. But that's in terms of the big data. At Google, we are now, again, ahead, right? So we're now moving on to this third wave of innovation. And that innovation is around machine learning. This person, anyone know who that is? Eric Schmidt, right? Yeah, executive chairman at Google. So this is what Eric says. Machine learning, this is the next transformation. The programming paradigm is changing, right? The way we normally write programs these days is you say, well, I need to go from here to there. So here are the set of rules, right? We want to say if this transaction is fraudulent or not fraudulent. Okay, then we say, let's check the address, let's check where they are, et cetera, et cetera. You have a bunch of rules, and then it said this doesn't meet those rules, so it is a fraudulent transaction. That's not the way programming is going to be, according to Eric Schmidt. What's going to happen? What's going to happen is that many of these decisions are going to be based on experience, which is essentially data, right? So instead of programming a bunch of rules into a computer, you show a computer a bunch of data and let it infer the rules by itself, right? That is essentially the idea behind machine learning. And machine learning is huge at Google, right? So we have an internal machine learning course that pretty much all, we're pushing all of the software engineers through, and you are seeing the effect of machine learning in all of our products, right? How many of you use Picasa as photo software? What happened to Picasa? It's gone, right? In favor of what? Photos. What is the difference between Picasa and Photos?
It'll organize everything.
Photos will automatically organize everything. You can go to Google Photos, right? And I was wearing this T-shirt about last week, and it said Ladakh. And one of my colleagues was, "What's Ladakh?" And I said, "Look, like I went to Ladakh like 4 years ago. And took my Google Photos. I didn't tagged anything. It was not, the photos were not even on my phone because this was 3 phones ago. I typed in Ladakh, and boom, all those pictures came up, and said, this is what Ladakh looks like, right? That is essentially a part of machine learning there, right? And that's essentially what we're talking about, right? Not programming computers directly, but having it infer things. And over time, you will see all of Google's products moving more and more and more towards machine learning. That's happening even now, right? Search, it's now the third most important thing in Google search. So Google search used to be just a bunch of rules. And the most brilliant people at Google worked in Google search, and they wrote all of those rules. And then recently we started doing them with machine learning, and we discovered that we could throw away a whole bunch of all of that code and replace it by machine learning. It's still not the number one input, it's the number 3 input, but remember that this is something that Google's been working on for 10 years. It's our crown jewel, and even there, search, and you all recognize it. When you do a search, the results you get are different from when your mom does the same search. And that's all coming out of this whole personalized search. You also, people who bought this also bought that, right? Where have you seen that? Amazon, all the e-commerce sites, they do that all the time. That's machine learning. Okay, but that's what a particular type of machine learning called product recommendations, right? You like this, you like that. What people don't realize is that spam filtering in Gmail is also a product recommendation, right? We recommend to you that this is an important email or this is spam, right? It's a product recommendation, right? Speech recognition, right? So when normally, right, the way you would do any kind of analysis, right, when somebody calls, is that you would say, you pick up the phone and say, press 1 if you want to do this, press 2 if you want to do that, they press that, and then you go to that phone tree. Many places that those are getting replaced, they want. Please tell us what you want. You speak a sentence, and you're basically directly directed to the right thing. So, like I was coming here, I needed to tell my credit card company, right, I'm traveling. I pick up the phone, they said, what do you want to do? I said, I want to issue a travel notification. There was no phone tree search. It went directly to the department that does the travel notification. So that's basically what we're talking about. You've seen it on YouTube with suggesting videos, route planning, etc. Okay, but machine learning itself, all of these things that we're seeing now, it seems to be like machine learning is new. Is it new? No. People have been doing machine learning for over 20 years now, right? So that's why in astronomy, for example, right? Pretty much, no one can sit and look at every star. That's just not possible. So for a very long time, analysis of astronomical data happened through machine learning. Okay? Many scientific domains, machine learning has been used for over 20 years. Right? But it's the fact that it's now mainstream that people are now recognizing that you see machine learning everywhere, and it's extremely important. In fact, my own journey in machine learning follows that exact trajectory. Right? I have a PhD in electrical engineering, right? So I used to work on heart mitral valves. So this is called a mitral valve, and you're trying to figure out if this valve is broken or not to decide if somebody's going to do surgery. Okay? So this was in 1994. We're doing machine learning on ultrasound images to figure out if the heart valve was broken or not broken. Okay? And then moved on to using weather. So that was in 2004. we're basically using machine learning to do weather prediction. Okay, so predicting hailstorms, tornadoes, flash floods, etc. Right? So that's all done with machine learning. In fact, one of the things in my past life that I worked on was the radar system in India. So you have the cyclone detection network in India. That's a bunch of radars, and building up the weather prediction system for that is something that my group in the US did as well. Okay, so that's again machine learning, right? But when you look at a weather forecast, you look at a heart diagnosis, you don't think machine learning, right? You look at the person in front of you, they have gotten augmented by that machine learning. That's what we're thinking about when we're talking. So following my journey on, I was doing machine learning with weather, etc., and then I got this opportunity to go build a data science team at a precision agriculture startup. You don't know what precision agriculture is? I mean, we talk about self-driving cars at Google, right? Say, hey, we can do self-driving cars. Tractors in the US have been self-driving for the last 5 years, right? So you have a tractor, it has a GPS on it. The farmer goes and parks the tractor in his field, and he switches it on, and it basically follows the entire corn, harvests the corn, comes back, right? All tractors are self-driving. You have planters, they're all automated. So you can actually program a planter and say, plant this thing 12 centimeters deep, and it will plant it 12 centimeters deep. You can basically say, here's the map of my field, and this part of the field has this type of soil. So plant this hybrid, and another plant plants some other hybrid. And you can do all of this hybrid planting. So that's called precision agriculture. So I built a data science team for precision agriculture. And it was in doing that I did it on the cloud, right? That was like 2014, right? So we did this on the cloud. And I realized that everything that I did at NOAA, the Federal Research Lab, things that used to take us 4 years, we were doing every 2 weeks at the startup. Incredible increase in pace. So why is that? Right? What makes things that take 4 years take only 2 weeks? It turns out to be something extremely simple, right? It all comes down to that massive infrastructure we're talking about. At the Federal Research Lab, we had 70 machines because we had to buy them all. Right? We bought 70 machines, and we ran everything on those 70 machines. So a job that takes 4 years on 70 machines, if you now gave me 8,000 machines, I can do it in 2 weeks. Does it cost me the same amount of money? Absolutely. Right? It doesn't matter, right? Whether you're buying 70 machines for 4 years and then they're obsolete at the end of it, or you're buying 8,000 machines for 2 weeks and it goes off to somebody else. Essentially, the cost is the same, but you get to do things much faster. Right? So that's the thing that you've got to remember, right? Sure, you can do anything that you're doing on the cloud. You can do it on a local server farm, on a private cloud. It'll just take you longer. And what value is that amount of time to do? Right? You can easily imagine that if something took us 4 years, we couldn't try out as many things. If something takes us 2 weeks, we get to explore the full spectrum of options. And so by the time we were done, we basically had built the most accurate rainfall system in the world. Right? And that essentially had a whole bunch of value. And then now, right, in 2016, I'm like, okay, now I know machine learning. I really have bought into the cloud. Where do I go next? And Google was the obvious next step, right, in terms of machine learning on the cloud and where you want to do it. So, but even things don't stop, right? Just because you can do something for 4 years and 2 weeks, things don't stop. So what we're talking about here is a second wave of cloud. The second wave of cloud, this is the idea, is that you get a machine, you get it for 2 weeks, and then you basically run your jobs on it. But that's the idea of reserving an instance and you owning this thing, right? But even there, you're talking in terms of getting a machine, starting up a cluster, installing software in the cluster, running things on the cluster. But where things are headed is completely serverless architectures. This idea that you have a job that you write, and you just give it to the cloud, and it will execute it on how many ever machines are needed, and give you your answer back in the order of minutes, regardless of the size of the job. Right? We'll talk about BigQuery. Regardless of the size of the query, you will get your results back in usually under 10 seconds. Right? How many machines is that on the back end? Who knows? Who cares? You don't care. Right? But the whole reason is that that same simple principle of economics, right? Whether you basically get tens of thousands of machines for a few seconds, or you basically have a few dozen machines for many hours over an entire weekend, it's going to cost you the same, get it in a few seconds, right? So that's the whole idea of this third wave of cloud. And so when I talk about all of these things, with MapReduce is the second wave. You're still going to be creating a cluster, you're going to be installing things on the cluster and going to be running them on the cluster. Then I'll talk about serverless. And the reason I'm going to talk about serverless is that's the third wave. That's where things are headed, right? In terms of data processing, it's this third wave, completely serverless. Remember I said MapReduce is no longer used in Google. We use Dremel and Flume. So Dremel is BigQuery, Flume and Millwheel is Dataflow. So that's why I'll talk to you about these two. And then the other transformation that's happening is around machine learning. So I'll talk about that as well. So before we talk about MapReduce, which is being obsolete, let's talk about what exactly MapReduce is. This whole idea was, the simple idea is that you do your computation on local data, right? You make your data local. And that's the whole idea behind HDFS, right? The whole idea is that you have a very large data set, you split it, and you store it on multiple machines. And then when you do your analysis of that data, what do you do? Each piece of analysis happens on different machines, and each machine processes the data that's local to it. Right? It does all of that job, and then basically all of those results get combined. That's a reduced phase, and then you get your answer. Right? So that's essentially the idea. You take your data set, you chop it into pieces, and then you do your map operations on local data, and then you combine the results. That's the whole idea behind MapReduce. And around MapReduce, once that paper got published, you basically got this canonical Hadoop framework that got written from it. Hadoop itself was too hard, so people built up a scripting language called Pig to make things somewhat easier. People built a data warehousing system that laid out a table structure on top of the data, that's Hive. And then you have Spark, which is recognizing that maybe some of these things can be done in memory instead of on disk. Right? So that's the whole idea behind Spark. But it's all this ecosystem that's come around MapReduce. Okay? So on the Google Cloud, you can do MapReduce jobs. Okay? You can still do MapReduce jobs, even though we're telling you that it's kind of obsolete. You should not be doing them. But if you have jobs that use Spark, that use Hadoop, that use these things, you can do them. It's called Dataproc. And it's still going to be the best place to run these kinds of jobs. So as an example, right? So this is the example I'm going to be using throughout the talk today. The idea is that I want to predict whether a flight is going to be late or not. Very simple problem. In order to do that, I have a whole database of flights. I have 5 million flights. And I know the departure delay of those flights, right? The distance that the flight is going to travel. The idea is that if a flight is like 1,000 miles, there's a chance that any departure delay can be made up. If the flight's only 300 kilometers, it's going to go up and it's going to come down. You're delayed by 15 minutes, you're going to be delayed by 15 minutes. So we want to basically go ahead and predict a probability. We want to predict a probability that this flight is going to arrive more than 15 minutes late. Okay? So in order to do that, we can do logistic regression. You can do this on Spark. This is the kind of thing that you're probably doing today, right? So just to show you that this is the kind of thing that you can do and what are some of the problems with it, right? So to do that, we have our flights data. I have it on Google Cloud Storage. Actually, while I'm talking about it, right, let me do this last thing, the second thing, to go ahead and I'll start my Dataproc cluster. So this is on the Google Cloud. I'll go to Dataproc. And I'll say, go ahead and create a cluster. I'll accept all the defaults, and I'll just say create. So my cluster is called cluster 1. It's getting created, right? So it's getting created. It'll probably take a minute, right, to basically create this machine. It'll be set up with Spark. It'll be all configured. It'll be ready to go. And I could have gone to that menu and said, I want 80 machines, 100 machines, 200 machines. I want some preemptible VMs, some regular VMs, all of that kind of stuff. So I could have done all that, create my cluster. But the important thing is my data are in cloud storage. So that's one improvement over having it on HDFS. With HDFS, it's where is the data? It's on that cluster. So I couldn't just start the cluster and run the job. I'd have to copy the data onto the HDFS cluster. We don't have to do that with Dataproc. Everybody see that, right? So it's just on cloud storage. I could start my cluster, I could run it, and I can go ahead and delete my cluster. So there is some benefit beyond just HDFS. So I start my Dataproc cluster, and then I'm going to submit my job. The job itself is basically going to be this. Okay, so that's the job that I want to run. Okay. So the job is your typical standard Python Spark script, right? I'm basically getting a Spark context. I'm reading text files, right? So I'm reading all of the files from 2015, right? Do you guys see that? I'm reading it from cloud storage. And then I'm basically going ahead and pulling out the departure delay, the taxi out distance, the taxi out, and the distance. So I have 3 fields, and I'm using the logistic regression class to train on the flight's data. And then I get my linear regression model. I set my threshold to be 0.7 because I want to do something with a 70% probability. And then I can save my model, and I'm done. Right? Does that make sense to everyone? This is a typical thing that you do with Spark. You're doing linear logistic regression with Spark. And now what I can do is I can go ahead and I can submit this thing to the cloud. And to submit this thing to the cloud, okay, so here's my train.sh. I'll basically go ahead and say gcloud dataproc submit to cluster 1, which is the name of my cluster. So that's cluster 1. It's started now. So I should be able to submit it. And I'll be submitting this logistic.py. Fair enough? Okay. So let me just do that. So I can do that. Sorry about the size, but all I'm doing is data analysis, 06 Spark, and then I can just say train.sh. So this is basically going to submit that job to the cloud. And if I go back here, right, I can go to my jobs. Okay, that's a completed job. Yeah, so here's the job that I just submitted, right? The job's running, and I'll get the logs. It's the usual stuff. And once this is done, right, this will probably take a few minutes. So once that's done, I'll have my result. Okay. But the thing that I want to point out is one thing. So far, so easy, right? We've simplified starting a Python Spark job, submitting it to the cluster. Once that's done, it's that one command line, gcloud delete the Dataproc cluster. And I can delete it, I'm gone. I'm going to get billed for the number of minutes I've used the cluster. That's it, right? So it's. I think you have a minimum of 10 minutes. So I'll probably get billed for 10 minutes. Okay, but that's about it.
So like deleting is the only way when you stop the billing, or can you stop the cluster?
You can also stop.
So you don't have to.
You can pause
again.
Right, but it takes you a minute to start a cluster. So it's not that advantageous. But of course, if you install other software on the cluster, then there is some benefit to stopping the cluster. So when you stop the cluster, you essentially just pause it. So you can do that. Right? But the thing that I want you to realize is that we had to start a cluster, submit the job. Right? And this is, even though it took only a minute and a half, this is kind of annoying. Right? Because when you start a cluster, you're essentially getting a cluster for yourself. Okay. And you basically, that's not the ideal thing. Right? The ideal thing is that you don't start a cluster with 8,000 machines. You just borrow those 8,000 machines and you go away. Right? So you shouldn't have to actually create a cluster. Right? And if you don't, that's what we mean by serverless. So if you can do things in a completely serverless way, with number 2 and number 4 steps not being done, it'll be very ideal for us. Okay? So that's basically where BigQuery comes in. So the idea is that with BigQuery, right, it's actually very similar. My flights data are going to be in BigQuery, and I'll basically have a notebook. Let's see if this job is done. Yeah, the job's actually going on. Okay. So here it is. So here's what I'm going to do. I'm going to go ahead and run this notebook. So this is a Python notebook. Okay. So I'll go ahead and I'll say run this. So that's a BigQuery. So that's my schema of all the flights. Okay. And then I can go ahead and I can run a statement like this. Right? So that's a statement I want to run. I want to select the departure delay, arrival delay, all of those things from the flights database, group them, right? And then basically get some statement. So this query, right, is actually two queries. I think you guys can realize, right? There's an inner query and outer query. This thing is going to get run on this 5 million flight database. Okay? And how long should it take? It should be less than 10 seconds, exactly, right? That's the whole idea behind a BigQuery, is that any of these things that you run, right? So it's running now. Okay. And there it is, right? So while this Dataproc cluster is still going, okay, finally the job is complete. I can now go to this cluster. Okay, I can click that cluster and let me just go ahead and delete the cluster. Okay. While that cluster was still going, right, BigQuery was completely serverless. I didn't start a cluster. I didn't have to delete a cluster. I just said, here's my query that I want to execute on my data. And it just happened. See the difference?
Choose a class to do logistic regression.
Uh-huh.
How are we doing that?
Okay, here I'm not doing logistic regression. Here what I'm doing is something called Bayesian classifier. So it's a different model, but you can, essentially logistic regression is a bunch of these statements on your data set. So you could do that as well, right? But here I'm doing something else. I'm doing what's called Bayesian. So I'm finding the actual threshold. And the idea is that if the flight departs more than 13 minutes late, right, that's when the arrival delay is going to be more than 15 minutes. And this particular model is called a naive Bayes classifier. So I'm using a different data science model. Okay, but just to show you that the same data set, a similar kind of thing that processes that entire data set, you can do it in a matter of seconds instead of having to create a cluster and delete the cluster. So this whole idea of, once you start thinking in these terms, then you stop thinking in terms of, well, private cloud and all of that kind of stuff, because you don't own any machines at all. You're not reserving any machines. You're not even thinking in terms of minutes or hours, right? You're just basically thinking in terms of jobs. Right? Here's a job that I want to run, and run it for me and give me the answer. Right? And those machines whatever machines processed our job, right, that did in this Python notebook, they're gone. Right?
Quick question, Isaac. So the cluster that I'm creating, the capacity or the specification that it requires, because like you have 5 million records, plus
right,
the kind of computing you require.
Yeah.
So is the user going to define what exactly you require, or?
With Dataproc, yes. You get to decide whether you want 10 machines or 20 machines or 30 machines, because you're going to pay for it. Right? So with Dataproc, you decide what machines you want, how many CPUs, how much memory. You make all of those decisions. With BigQuery, you don't make any decision. You say, here's my query, I want you to run it. And it will basically run it on as many machines, on the most powerful machines, get you the results as quickly as possible.
So in that case, what is really cluster representing? Because I'm not driving machine capacity, I'm not defining what kind of machine. So what is the cluster representing in this scenario?
In which scenario?
So you got a query which is running.
Okay, there is no cluster in BigQuery.
Okay.
With BigQuery, you stop thinking in terms of clusters.
You don't have that at all.
You don't have that at all. All you have is a query, and those queries going to get run on your data. So you have your data, and you have a query. That's it. It'll auto scale. It'll auto scale. It'll do everything, right? You don't think it. You never actually touch the hardware at all.
Preemptively, it will say that we need more memory or more CPU power, and then it will auto scale.
Yeah, exactly. In fact, it actually does it even before, because it has this. The parsing engine is smart enough to realize how big a cluster it actually needs, how many machines it needs.
So BigQuery take care of the SQL-like statement here.
Correct.
But what about the actual where you calculate? Is that done?
I'm doing that in Python.
As in, where is that code executed?
This code is executed in this notebook. So this is the Python notebook. Okay, and this is called Data Lab. And in the Python notebook, you have this magic SQL string, And so what that does is that executes a BigQuery. And then when I execute the BigQuery, which is actually kind of cool, once I execute, so this is the BigQuery. BQ is BigQuery. So that's a Python package to do BigQuery. So I'm query this departure delay query, which is this one. I'm converting it to a pandas data frame. So the two data frames are pandas data frame. So now depth delay is pandas. And at this point, you're now with traditional Python dealing with pandas. So you can do everything you can do with pandas here, except that you've gotten this data frame as a reduction from your massive data set that's in BigQuery.
My question was this: where is this code executed? This Python code, right? Is it like executed on the BigQuery?
Oh, it's running on. Okay, good question. This notebook I can run either on my local machine. So in this case, this notebook is getting executed on localhost, which is my laptop.
Okay.
But I could take this thing and run it on a cloud machine, and it will get executed on the cloud. But these are cheap, right? So I can as well run them on my local box.
Are you sending the query to the server?
I'm sending the set, yes. BigQuery always runs on the BigQuery servers.
So it's not a good idea. So if you want to run it on a local host, and if you want to get a lot of data back, it's not a good idea to run it on local host.
Yes, that's true. Because this two data frame will basically download it all right, to your local one. So yes, in that case, you want to run it on the cloud, or you want to do it in views. You want to do something smart. You want to do it in batches.
So how do we determine the cost associated with this? In the other case, we know it's the CPU, the time. And
Right. So the easy way, there's on the, okay, so GCP pricing calculator. So you can go there, okay, and here's a pricing calculator. So if you want to figure out how much it's going to cost, you can say, here's a BigQuery. And I'm going to say, okay, now it's going to charge you for both storage and for query, okay? Because you're storing the data. But the storage cost is essentially the same cost as storing it in cloud storage, which is similar across all platforms. So it's cheap, right? So cloud storage pricing is cheap. So for now, I'll just say I have 100 gigs, right? Whatever it is, not much. It's a query that you're worried about, right? So let's say I'm going to run 1,000 queries, right? I'm going to process 1,000 terabytes of data. You're going to get charged based on the amount of data that you're going to be processing. So I'm going to assume here that I'm processing 1,000 terabytes. Right? This is pretty significant. And then we can divide it by 1,000 to figure out how much 1 terabyte costs, etc. So I'll just add this to my estimate.
1,000 terabytes. It's a single query that you're talking about. Right?
It doesn't matter whether it's one query or 100 queries. You get charged for the amount of data that you process.
Okay.
So if you have one query that processes 1,000 terabytes, right? Or you have 1,000 queries that process a terabyte each, this is basically what it's going to cost you.
Is it related to the storage pricing? Because I already mentioned 100 GB of data.
Right.
I'm going to operate on that 100 GB of data. The storage pricing also, the query pricing also should be for 100 GB.
No, not necessarily. The query pricing is based on how much the query processes. And you have to store your data in BigQuery.
Convert them into different formats.
It's
Yeah.
$5 for a terabyte of columnar data that was parsed. That's how you do this, right?
Yeah.
So BigQuery, just to add to that, right? So you have Redshift, right? Redshift, you're doing the entire infrastructure bit, and then you can use the Redshift services. This is a managed service by Google, right? So the cost for running BigQuery is two parts. One is the cloud storage, and the second is the querying cost, which I told you was 1 terabyte for. So basically, this is how 1 terabyte is $5. Right? You can
And the first terabyte is free. So first terabyte of every month is free,
You can further reduce that
which is why I did 1,000 terabytes, because if I had done one, it would have set the cost to zero. Right.
But you can reduce that further by having the caching and everything on as well
Right.
in BigQuery. Right? So
You mean
the
It's
query-
automatically cached and
Yes.
so on. So
This is computing.
yes, go ahead.
Let's say we are uploading a data of 100 GB, but there may be categorical features which we convert it to one-hot encodings.
Okay.
Their size increases.
Right.
The query has to process a larger data.
Right.
In fact, we uploaded a
Yes.
smaller amount, but when we are converting into different formats, the size
It could be bigger, whatever. Or no, but the point was I had to put in something for the pricing, so I just put in 100 as just but it could be whatever, right? So you're going to pay for the storage, right? And that's going to be regardless. If you run no queries, you're still paying for the storage.
So 1
Because you put
terabyte
your-
per month is free.
I'm sorry, 1 terabyte per month.
It's a monthly quota.
Monthly quota of 1 terabyte. So if your data is small enough, again, we want you to use it. So if your data is small enough, you're playing with it, You don't reach 1 terabyte, it costs you nothing. And again, $5 a terabyte. Okay,
One
so
small query. The processing that we did right now.
right.
How much GB would that have cost?
Yeah, so okay, that's a great question. So we can look at that too. So what I'm going to do here is I'm going to copy this query. Okay. And so here's the select statement. So this is the one that I just did. So there is a BigQuery console. So bigquery.cloud.google.com. And on the console, I can say I want to compose a query, do that, I'll run the query. And notice that it was cached, right? Why did it say it was cached? Because I did it in the data lab. It knows that it's the exact same query. So the cost of this query is 0, right? Because it's a cached result. We don't charge you for cached results. So you only pay the first time, right? For, I think it saves it for like 10 days, right? So for you pay for it once every 10 days that you run this query, as long as the answers don't change, etc. Right? So this particular query, so let's not cache it. So I'll show the options. I'll say don't cache it, and I'll run the query. It'll tell us how much data it processed. Okay. So it processed 87.3 megabytes of data. Why is it only 87 megabytes of data? The actual data set, right, is larger, but I happen to be pulling out only 3 columns from that data. Actually, only 2 columns from that data: arrival delay and departure delay. Right? I'm pulling out only 2 columns. So even though that data set is large and it has like 50 or 60 columns, I only processed 2 over 50 of that data set. Okay, and that's what I'm going to get charged for.
One last question. Let's
Yes.
say I want to try it out.
Uh-huh.
I run one job.
Right.
Is there a real-time billing? I can see how much it costs me so that I can get a.
It's not exactly real time, but within a day you will be able to see it. If you go to your console, you can go to billing. Okay, and it actually easier way is to just go to the home dashboard. On the right hand side there'll be a billing, right? So there's my billing, and as you can see, it's cost me 36 cents, and that was probably I don't know what it was. Okay, but that's like 3 cents. 3 cents for storage, and the rest of so that's only BigQuery charge on there. Okay, and I've used 1.6 gigabytes of querying.
So you used to have the fusion table in the past. We used to have.
I'm sorry?
Fusion tables.
Okay, right.
So
Yeah.
even in fusion table, I can do some of this.
Right.
Is there any guideline on what you should use for?
Yeah, fusion tables for small data, and BigQuery is for large data sets. BigQuery is the one that's actually integrated with the cloud. And so you can do data proc, you can do cloud storage, you can do all of those things. Fusion table is very much for app engine, for small applications, and that's about it. Right? So it's not scalable. Yeah. Fusion table is not a scalable solution.
So if the data set is small, I should still go for fusion table.
Yeah.
Rather than coming to basics.
Yeah, use BigQuery if you need to combine it with other things. Right?
So here, because it's driven by the size of data I process, it says $5 per month. So what is this per month?
Oh, because I was assuming I'm going to run this query over and over again. Right? It's a repeatable model. Right? I'm assuming that it's going to be 1,000 terabytes per month. Was my pricing calculation? We're trying to estimate a monthly bill, not a job bill.
BigQuery supports querying from a range of tables for days.
Correct.
I can run it for a table that I got today.
Yeah.
Is the caching smart enough to understand that the data has changed when I
Yes.
query it, or should I have to?
Yeah. So if the data changes, then it won't be cached. Right, yes. But yeah, and it's smart enough to do that because it knows that typically what you do is you drop a table in the other table. Right? So it knows that.
So there, can you notify when I might have 100,000 fields in that, right?
Yeah.
But the query I'm running I'm only bothered about those. So
Right.
the caching is looking at, it can only look at certain fields where I am bothered about. Or?
Not that smart. Not that smart.
And are we charged with the uptime on the iPad and notebooks like running data lab?
If you run in Data Lab, the way I'm running it on a local machine, so 0 charge. If you run it on a cloud machine, right, then you're charged for the cloud machine. Data Lab itself is free.
It's free.
right? But you're charged for the machine that you're running it on, right? Either you pay for it because you bought the laptop yourself, or you pay for it because you're renting it.
You're running data lab on the Google servers, like the cloud.
Okay, so you're running it, then you're being charged for the cloud machine.
As long as the notebook is running,
Okay.
are you charged for that?
Yes, but you can stop the machine, right? You can stop it.
And like, does Google have a policy shutting down a notebook if it's not running, or does it? It's on us to shut.
It's on you.
So does it always expect data to be in tabular form?
Yes, BigQuery is tabular data, but tabular data is better than normal table data because your data can be nested and repeated fields. So it's somewhat hierarchical, but not full blown, right? But you can have nested fields. So you can have a JSON thing and you can upload it to BigQuery.
Are subqueries cached separately from the full query?
No, it's a full query. It's just a query, the entire
So
query is
if the
cached.
same subquery is used in multiple queries, that would
Then you probably want to run, so it's not good.
Just to add to that, we use BigQuery in the past. You have used data, take it down as is, and then your cost will go down because you are only querying that. Keep in mind.
Yeah. So partition your data. You can either split it by tables, or partition it. That's another way to do it. And that's the way that you want to keep in mind that we charge you for the amount of data you're processing. So figure out a way to reduce the amount of data that you process.
we can have like multiple queries as long as we are processing the same amount.
Right, exactly.
Most of the time, like, if you have temporal data, you will be querying the recent data.
Yeah.
So it's better to keep it.
So essentially, right, we kind of talked about something. BigQuery is like interactive analysis. It can go up to petabytes with a SQL-like language. You can also write user-defined functions. So you're not just limited to count and sum, etc. You can write your own functions. Those typically are map functions. You can also do, essentially, let's say, do serverless data analysis. Right? As long as your data analysis is SQL-like. Right? What if it's not SQL-like? What if you want to have a while loop, a for loop, right? What if you want to do something beyond SQL? We still want you to be serverless. That's where Dataflow comes in. So Dataflow is your serverless data pipeline. And here's the deal. Anything that you can do in Hadoop, anything that you can do in MapReduce, you can do in Dataflow. Plus, you can do a whole bunch of other things. Okay. So again, as I said, 2006 was the last time we used MapReduce at Google. This is why. Right? A combination of BigQuery and Dataflow means that we don't use MapReduce anymore. Okay. So how does Dataflow work? The idea behind Dataflow, and I'm showing you Java, but Python also exists. Right? So actually Python exists. It went beta like just this week. Okay, so we have Dataflow in both Python and Java. I'm going to show you Java, but remember that this works in both Python and Java. So the way it works is that you create a pipeline, and in this pipeline, I'm reading from cloud storage. I'm applying a filter, the results of that filter go to this group, go to this filter, go to a transform, and then I'm writing it on. And of course, each of these returns what's called a parallel collection. So I can take that parallel collection and apply another pipeline to it, right? So I can basically, my pipeline can branch, it can do multiple things, it can do, imagine like a graph, that graph there, but that graph doesn't have to be linear and straight. It can be up, it can go off, it can have conditionals, you can have loops, you can do all those kinds of things, right? So you can build a pretty complex pipeline. Now here's a cool thing. Here, each of these classes, filter, group, all of these things are user defined. Here I'm right, they're Java classes. In Python, these are generator functions, lambda functions, right? Just functions. You write your function and you say, this is my step in my pipeline, right? And each step processes the input data, does something, and writes it out. Now, this particular step, I've wrapped it in a parallel do. What I'm telling Dataflow is, auto-scale this for me. So it's going to get read. Every line of it is going to go into this filter in parallel. So what's going to happen is each line is going to come in and it's going to get split out into multiple machines and just get pushed through all at once, right? In parallel. all the results basically go into this group. It's going to all get done. And then the results of that group go into this filter, which are again fan out, do it in parallel, push it through, come back. So you get to choose what steps of your pipeline need to be done auto-scale. You take this pipeline and you submit the job, and that's it. Right? Everything else gets taken care of. You don't actually start a cluster, delete a cluster, do any cluster management at all. This is all about you write the data pipeline, either in Java or in Python, and you say Dataflow, execute this for me. Just like you said BigQuery, execute this query for me.
This code that we write, can we use external libraries?
Yeah, absolutely. Anything. You can have third-party jar files, and it's basically that thing that you're submitting. It's very similar to like an archive file that you're submitting. Typically, you do it with Maven, right? And you basically have your main class, and you can have any third-party classes, right?
And the first step where you are referring a file from root storage to the BigQuery query as well.
Yes. So the input can be you can read out of a BigQuery. You can do BigQuery IO. You can also read out of PubSub, which I'm going to talk about, which essentially lets you read out of a real-time stream. So if you have an IoT stream, data coming in, or stock trade data coming in, you can read out of that. Okay, you can read out of Bigtable, which is this high throughput database. So there are a variety of input sources.
So what basically does the apply function there expect?
The apply function essentially expects this thing that it's a P collection. It requires a parallel collection. And text.io.read gives you a parallel collection. That's all.
Okay, so is there an API there for writing the BigQuery?
Yeah, sure. So you can, yes, it's a class. So you just implement that class. It has a bunch of functions. You just implement those functions, and you can read out of something else.
So even that will be done with text.io.
Yeah. So you can look at text.io, how it's done. And the thing to realize also is that all this code, this API itself is open source. It's called Apache Beam. Okay, so you're not actually tied into the Google Cloud. When you use Dataflow, it's an Apache Beam, it's an open source API. Flink is an implementation of this, as is Cloud Dataflow. So what we are competing on is that our implementation is going to be better than what you get, but you're not tied in. So you can always take it and move it and run it somewhere else. So as I said, right, you can basically take this exact same pipeline that you had, replace a text.io.read with pubsub.io.read, and now you're reading real-time data. Right? So suppose you're getting stock market data and you want to read it. This is what you do, but then you need to figure out when do you write. So typically what you do is you take your input data and you apply a windowing function to it. Here I'm applying a window of 60 minutes. You don't see an every, so the default is 1. So essentially every minute, I'm taking the last 60 minutes of data and applying the data pipeline, whatever the data pipeline is, right? So if my data pipeline is basically taking it and doing some computation, that computation is being done on the last 60 minutes of data. The output goes out, and then 1 minute later, repeat the job. 1 minute later, repeat the job. It's as simple as that. So it does both real time and it does batch. So if you have some data that's batch data, you have some data that's stream data, get it into Dataflow. You can do filtering, you can do grouping, you can do windowing. Filtering and grouping, you could do MapReduce, but windowing, right, is very good. So as an example of showing you something that you cannot do with MapReduce, so what I'm doing is I'm going to go ahead and create this model that's going to predict, is it more than 15 minutes late? Same thing. But to do that, I'm in addition to the departure delay and the distance, I also want the average departure delay for this airport at this hour. The idea is that if you are flying out of New York, like JFK, at 5 o'clock in the evening, every flight is going to be on the tarmac for an hour and a half. Right? The runway is just completely backed up. But the airlines, they know this already, so they put the schedule, they add an hour and a half delay, and they say, you're going to arrive only at 9 o'clock. Right? So you're not going to be late because you're departing from New York, where you know it's going to be an hour and a half to get into the air, right? So we want the delay for this airport at this time. So I'm currently, this plane is scheduled to depart at 5 o'clock from New York, right? 1.5 delays average, normal. So I want to know the average departure delay as part of my training data. Does that make sense? In addition, if my plane is going to be taking off, right, there's some weather, right, in Mumbai where I'm going to land, I can look at the average arrival delay right now. This is historical. This is real time. You guys get that, right? So this is going to be my training data set. And I think you guys are going to realize this is something you cannot do with MapReduce. Right? We're mixing real-time data, historical data, doing windowing, creating a training data set, and then I'll use TensorFlow to do the training. Okay, that I'll do next. That's why I kind of hidden this. I'm not going to do this yet. Here, I'm just going to show you how to use Dataflow to create this pipeline, right? And to do this, here is my Dataflow job. And by the way, this is all, it's on GitHub. It's all open source. Okay, so if I think Anuja is going to be mailing you a link to the deck. So all these links are there. So you can feel free to go take a look. Okay. So here, what I'm doing is that I'm going ahead and where's my pipeline? So here's my pipeline. Okay, so this is a pretty complex pipeline. Remember that I'm doing windowing, right? Multiple ways and all that. But even here, right? I'm essentially going ahead and let's start with, so the first part, okay? First part, this part here is computing the average arrival delay. Okay? That is creating the average arrival delay for this airport at this hour. So to do that, I basically go ahead and say, get me the from airport, get me the departure hour, get me the departure delay, make it a key value pair, and output it. Okay, so I'm just outputting for this arrival, for this, so each flight, I'm basically throwing that out and computing the mean. Okay? And then I'm taking that mean and I'm writing it out as a CSV file. That's pretty much it. So this is a little custom. This is already built in, like mean per key. So similarly, I can go ahead, I can do the other one, okay, which is, for every flight, go ahead and add those two pieces, right? The arrival delay and the departure delay. Okay, so I'm just adding those and I'm writing them. The point being that each of these things is essentially a bunch of applies. This is a more complex, somewhat more complex diagram, and you look at this diagram and we go ahead and launch it. So let's look at, to launch it. Here. So to run on cloud, I'm basically going to say, I want to run this class create training data set, and I'm going to basically pass in where my input is, 2015 star.csv on cloud storage, and that I want my output in this directory on cloud storage. And similar to the way I did Dataproc, I can simply go ahead and I can run it. So 07 Dataflow and run on cloud. Okay, so it's going to just, it's compiling all of the code and it's basically going to run it. And so now this, like Dataflow with BigQuery, typical jobs take on the order of seconds. With Dataflow, typical jobs take on the order of minutes. Okay, essentially because your jobs tend to be more complex. They tend to have all kinds of structures and recursion. It's the program. Right? It's a program. It's not just a SQL query. It's a series of steps. And each step may take a few seconds maybe, but sometimes just the reading of the input and writing of the input, right, will take you a bit of time. So we can go again to our cloud console and we can monitor this job. So let's go to Dataproc. Oh, Dataflow, sorry. So that's my Dataflow. Notice that this job is currently running. And here's my job. And this is my pipeline that's being executed. Right? So I'm reading 2 inputs, right? And then basically going ahead and putting them and parsing the flights, getting an airport per hour, doing the mean per key. I showed you that piece of code. And then that basically goes to 2 places. One of them gets written out, the other gets read, right? And then, like adding some information and writing it all out. Okay, this diagram essentially got built from my code. Right? I said, here's the job. As soon as I submitted it, it could look at that, it could build this diagram, and it will give me essentially status on where we are inside the job.
So if there's an error in any step, it will show.
It will show us.
It's interactive. I can.
Yeah, so you can basically, it's an interactive thing. You can go ahead and you can click on this thing, right? And you can say, okay, this thing, no, or no, here, this one has succeeded. So summary, right? It took 40 seconds to do, right? Et cetera, right? And I can also stop the job if I wanted. So I can click on any of these things as they go along, okay? And it will tell us, right, what exactly that thing did. Okay? So as you can see, this guy is working, and as it continues, it'll tell us, right, like what each of these things are doing. You can also look at the logs of that particular step. Yes?
Does it give an estimate of time it's going to take?
Not really, because it doesn't know, the exact thing that you're doing. I mean, maybe inside your code, you're doing a math.log or a math.tanh, right, which is very common in machine learning. Those things are expensive operations, right? All it can say is, here's a step you're going to do, and I'm going to execute that function for you.
At least the progress percentage, something like that. I see, kind of, I get an idea that this is the step it is that.
Right. It tells you how many elements it's processed, but it doesn't know. Again, remember that this is a real-time tool as well. It doesn't know how many things are going to come in. Okay, so that's something that you have to add in. It'll tell you that I've processed 300, and you have to say, well, I have actually 3,500, so it's now about 10%. You can do the machine learning.
No, that's a very interesting part, because see, one execution has happened. Now you know the profile.
Right.
Then after that, you can tell the where the optimization.
If you're talking about execution, like the job being completed, but this is like this is reading from real-time data as well, right?
Right.
So like, as long as it keeps on running, it will keep on reading data and keep on.
In this case, I didn't do the real time. I did on batch. That's why I said it finished. If I was reading from PubSub, you're right. It would continue, and it tell you how many times it has done it. It'll tell you the number of iterations as well.
But for PubSub, we did specify a time duration, the last 16 minutes.
Right. Yeah, you set 60-minute windows,
Right.
but the entire pipeline never actually stops.
Correct.
Right. The pipeline continues. The pipeline is executed every minute over 60 minutes a day. Was our idea.
So the dotted lines are processes which are happening in parallel or
Which dotted lines?
not?
No. These are logical flows.
No. The box, basically some greens are solid and some greens are dotted.
Right. Exactly. Yeah. These things are being auto-scaled.
Can you go back to the shell script that you used to launch?
Can I go back to shell script? Sure. So here's the shell script. Oh, no, not that shell script. Here, this shell script.
So why do we have to mention the input and output here? I thought you can mention the source of your data in the text IO.
You can, right? But I don't want to mention it in my text, so I read it out of the command line.
Okay, so can I override? So if I mention an input and output there, and if I mention another data source in my text IO API, will that?
No, it depends. The way I do it is in my code. I ask for the command line. There's no magic there. So if I were to go to the code, let's just go ahead and go to the code itself. So here, if I go to the code, there's absolutely no magic. I explicitly say, where is my input coming from? So when I go down here, okay, so I basically say, get me the input directory. The default is my local test file, Okay, so I will call the get input here. I would say options get me the input. Okay, I did not have to do that, right? I could have just put quote and put in something, and that would be what it is. Yeah. So there is no magic. It's explicit.
Find the credentials in Java from where it is reading the credentials to upload.
Oh, the credentials, because I'm launching it from my command line, it gets it from gcloud SDK, correct.
And is there any process to debug this?
Yes, absolutely. So you can look at the logs, right? And you can add things to the logs. You can have different levels. So the logs are the primary way that you debug it. The other thing that you can do is that you can run this locally, right? You don't have to run it on the cloud because this is just a main program. So you can right click and run as in Eclipse.
Yeah.
Okay, and then you can basically debug locally. That's kind of why in my input you see that my default, right? Because I did a right click and run as. That's why the options, if you noticed, my input was a very small data set on my local directory. That way I can just run it locally, and I can put debug statements, I can put breakpoints, I can do whatever.
So while processing anything in parallel, so is it something like how it will debug any parallel things there?
Yeah, so you will get all of them, right? You will get all. So in the local machine, it does it on 3 threads. Okay, so it's like threaded debugging.
Can I put this thing onto my continuous integration and run that as please?
Yeah, you should be able to, because it's again just these are all regular Java classes. Right? Regular Java classes, you can write JUnit tests around them. You can do everything that you can do normally in Java. You can do here.
If my data is not clean, it can, some of the pipelines can stop.
Correct.
That has been known from the data flow that you showed.
Yes, from the log, so you'll basically get an error that says exactly what it is, and then it's up to you to add enough information to that exception so that you can basically debug it. So again, you write the Java code, you launch the pipeline. That's pretty much it. And that's again, I hope you guys all see that what exactly we mean by serverless here. Right?
So
there's no clusters here at all.
But does GS have also an API so that you can control that how much machines should it run on?
No. Yeah. Basically, again, stop thinking in terms of machines. In BigQuery or in Dataflow, we don't give you control over the number of machines because that's beside the point. We'll auto-scale it the maximum number possible. Right? Give you the answer as quickly as possible. It doesn't cost you, it's not cheaper to run it on fewer machines. I think that's the thing that you have to get out of your head. It is not cheaper to run it on fewer machines. We already have those machines, right? We might as well use them. Is the whole point.
No, but things can happen, right? So I'm processing for a first week only of a month, and I don't need any more.
Right.
So whatever the time for which this processes, you calculate that much amount of money.
Right. So whether it's so it's just those fractions of a second is essentially what you're paying for. It's not going to really matter, right? Whether you do it on many machines or a few machines.
It is better than creating a cluster because they have to keep in mind of stopping it, restarting
Right.
it to save billing.
Exactly.
This runs and
You're just charged for what it costs. That's it.
it's much better.
There is no cluster management at all.
Faster than, let's say, it was Lambda.
Lambda is more like our app engine, which is like the web thing 2008. This is like way this is data processing.
So one important aspect when you're taking control away from machine thinking is about basically now user doesn't have any control how machine to be configured. So is Google looking to provide some sort of assurance in terms of the performance? Like,
Yeah, there are SLAs around all of this stuff.
So you say this is the size of the query, then we tell you sub 5 seconds.
Right, exactly. So we have those assurance guarantees for those things.
How is the pricing here? Is it like based again on the data processed plus?
It's based on compute and
Compute.
compute. It's primarily based on compute. Yeah. So the idea is that BigQuery is around declarative, it's data, right? Dataflow is around programming, it's programmatic, it's compute.
Is it based upon how much compute, like time spent on the machine, or so like?
Time spent
there
on the
is
machine.
Some operations where we are waiting for a real time stream to come in. So for that way, we won't be.
Yeah, as long as the machine is blocked for you, you pay for it. Yes.
It's not really compute.
When I use BigQuery in my pipeline, will I be priced separately for the BigQuery part and the
Correct. You will get charged for all of the resources that you use. So if you run a BigQuery query and you read into it, you're charged for the BigQuery query, and then you charge for the data.
In the logic, there could be bursts of computing power requirement, and
Right.
there could be lulls. So,
Absolutely.
in the lulls, does it average out or?
Yeah, you basically it'll shut down those machines and you won't pay for them. Right? It's auto scaling. Right? So at bursts, you will get a lot more machines, and then when it's not bursty, you'll lose all of those machines.
In the same data pipeline.
In the same data pipeline. Each step of the data pipeline is auto scaling.
So it will come down to one machine.
Typically not to one, yeah, right.
Of that order.
Okay, yeah. So it will get auto scaled and it will come down to minimal to maximum, right?
The question would be when you have a PubSub model for the input.
Right.
How do you determine when is that peak and when is
Oh, basically, it's one of these things that's adaptive, right? So basically, it starts doing the query. It says, oh, these machines are getting overloaded, so let me add more machines. But all of this happens in very fast.
For us to estimate how much it will cost in such cases.
Right.
I think that's where Rafi was also asking.
Correct. So probably the best thing to do is to go ahead and run it, and then find it. Right? Again, a single thing, right? This entire query that I ran, it probably cost like 23 cents. Right? It's not you basically will start paying only when you do this repeatedly. So it's not that, you're not going to be out hundreds of dollars if you run a single pipeline. So run the pipeline, find out how much it costs.
I remember the pricing around GCP where data in and data out used to be charged, but it was free inside the Google network.
Correct. Yeah.
Does that same thing
That
apply
same
here
thing
also?
applies here.
From Google Cloud to here, you don't have to pay.
You would have to pay for egress. Yeah, getting the data in, you don't pay. Getting the data out of Google Cloud, you pay. Within Google Cloud, you don't pay.
Is there any benchmark available or Google has done if you do run the, let's say, equivalent thing onto Amazon? AWS?
There is no equivalent of this in Amazon.
I'm seeing from a user perspective.
Right.
So that's a
So there's this taxi cab data that people have done. So you should go look at it. Right. So just do a Google search on taxi cab data. Right. Comparison between GCP and AWS. So this is an independent guy in Europe, and he did exactly this. He took the taxi cab data, including cost. So he basically took the taxi cab data, he did the analysis, he talked about what was involved, how much it cost, right? How all of that stuff. He wrote a blog post for each thing. Okay, so it's well worth going and reading. Just do a search for it. His name is like Mark L something.
And he's not from Google.
He's not from Google. So again, as we said, right, transformations on the data side is all about serverless. It's all about getting things as quickly as possible with no machine handling at all. The other transformation that's happening is around TensorFlow, machine learning. So why would you want to do, like we said, why do you want to do data analysis in the cloud? It's all about economics, right? But as well, get a bunch of machines, get your job done faster. Why do you do machine learning on the cloud? It's not about economics. It's about something else. It's because if you want high accuracy in machine learning, you need a very large data set. Okay? There's no real working on it. You want good high accuracy machine learning, you want a large data set. And the reason that accuracy increases with the amount of data is because of a few things that have happened in the machine learning research community in the last few years. One of them is this idea of what's called deep networks. A deep network is like a neural network with many, many, many layers. It turned out that people had deep networks for a long time. Okay? So you could have had a neural network with multiple hidden layers. The thing was that it wouldn't actually converge very well, right? And if you had a really large data set, it would just get stuck in local minima it wouldn't work. These days, with larger data sets, better like optimization methods, etc., those things are turning out to work well, right? And you want to do deep networks, you need them to be blazingly fast, and so you need to run them on dedicated hardware. That's why GPUs and TPUs come in, right? TPU being a TensorFlow processing unit, which is essentially very highly customized to the exact machine learning workload. It's an ASIC chip for machine learning, right? Rather than reusing a GPU, which happens to have many of the functions that a typical machine learning workload would have, right? But it doesn't have some, and it has many others. Right? The other thing, of course, is the whole idea of auto-scaling. Right? You want to basically be able to auto-scale to many, many, many machines. Okay? So if you have a very large data set, you have a deep network, you're basically talking about a really, really large compute problem. And when you get a really large compute problem, then that's when you need auto-scaling to distributed machines. A significant portion, I said Google buys 1/5 of every CPU that's produced. A significant part of our workload, we don't say exactly how much, is around machine learning. Okay, that's the reason. The machine learning is what essentially uses up a huge portion of the workload on the Google Cloud, okay, because it's really, really, really expensive. And there's no way around it, right? The way you get accurate machine learning is by solving this massive compute problem. So you want a very high accuracy, you want to use large data sets, deep networks, dedicated hardware that's auto-scaled. And that's essentially what cloud comes in.
I'm just curious, this custom chip that's being done, is it Google's internal IP or is this some type
It is Google internal IP, yes. And the idea is that we'll have it on the cloud for others to use as well. So you can submit a job that will get executed on Google's hardware. Okay, that's what cloud is. So when you're talking about machine learning, right, there are a few levels of machine learning. So the easiest thing, the most bang for the buck, is if you don't have to do any training yourself. Right? If you can just come to Google and say, give us your model, right? That's amazing. So machine learning APIs are just that. So on the Google Cloud Platform, we have machine learning APIs. These are APIs that are trained by Google. So we've trained them using TPUs, using our large data set, right? So when you talk about Google Translate, for example, we've basically gone ahead and found documents that happen to be in 2 languages. There's a whole bunch of them on the web. And we took all of them, and that's basically become our training data set. What are the chances that you can come up with that bigger data set? Right? So it's kind of good if you can basically take advantage of our data set, our training, and simply use that model. That's what the machine learning APIs are. How many of you have used this app? Pretty cool, right? Yeah, I mean, it actually even works offline in many countries, right? You can basically point a camera at some foreign text and it'll translate for you. What does that involve? Behind the scenes. Image processing, optical character recognition to find those letters, translating that language, right? No, first of all, detecting that language many times, right? Is it Chinese? Is it Korean? Is it whatever? Many languages use the same script, right? German and French and Spanish is the same script, but they are different languages. So detecting the language, doing the translation, and to me, the coolest thing of all, fitting it all into something that's the same size. Similar kind of font, and basically displaying all of that. That's all there, but all of those pieces are open. Right? So you have the Vision API, which will let you do character recognition. Right? So you can do OCR on any image. You have Translate API, which will let you do translate. You pass in a string in one language, that will give you back a string in another language. You can pass an image and get a label, which is what is in this image. Okay? You can do safe search. So this is a very, very, very popular use case. So any company that asks people to send them images and automatically display them on a map, display them somewhere, do a Twitter feed, whatever, you want to make sure that you're not tweeting unsafe content, right? So that's part of the Vision API.
So these pieces I can plug into my regular programs that I write on websites.
Exactly. So this is all REST APIs, web APIs, right? So you basically say, here's my image, tell me what's in it. Or here's my image, tell me what text is in it. Or here's an image, tell me if this is safe or not. That's it. And you're not actually doing anything else, you're just calling a method. Yes.
I wanted to use speech API, but it is in limited preview right now.
No, not anymore. Not anymore. It's gotten beta. It is now beta, right? So, for example, right, here's this. So, for example, this is the speech API, and the speech API was built on a web page, and all that the web page does is that it listens to my microphone and passes the result of my microphone back to the Google Cloud in REST API calls. It does this in bursts, and each burst then basically gets translated, right, or transcribed, and gets displayed in this text box. And so imagine that you can take this essential technology and put it into any of your applications.
Nice.
Fair.
In Google Translate, you have that feature in apps where
Right.
you can write in Hindi.
Exactly.
Converts it to English and just real time it displays.
Exactly. And all of those pieces you can put into your apps too, right? Essentially what Google Drive does, what like 30% of Android searches now are on voice. 30% are voice, right? And we only think it's just going to increase. Who wants to swipe and type and all that? This is pretty darn accurate, right? So you're going to imagine that 3 years from now, if you ever build an app that asks people to type in stuff, they're going to move to some other app, right? How many of you have used Google Forms? Forms. Yeah, I mean, this is where you can go ahead and create your, like, so I'll show you what it is.
Speech enabled now, is it?
No, it's not. It's actually pretty cool, right? So I'll show you what I'm talking about. So a Google form is a form where you can basically create a form. You can send out a survey, ask people to it, right? So here is my form. I'm going to type in a question. Okay. So my question is, okay, are you free for lunch? And notice that it automatically suggests yes, no, and maybe as my answers. I do not have to type them in based on the question. I'll add one more question. Okay. Which day works best for you? Slow. Okay, it's slow. There it is. It took a while. But notice that it automatically suggested answers Monday, Tuesday, Wednesday, etc. Point being that it's adaptive, right? It's figuring out what I'm typing, what the possible answers are, and showing them. This is what the UI of the future is.
I mean, just out of curiosity, can you type like who will be the next US president?
Sure. Let's see who will next. Let's see. I don't know. It's awfully slow. So
the problem with the speech today is the noise around the
guess not.
separate out the noise, right?
Yeah. Oh no. Okay. Yeah. Let's try it. It's actually pretty good even with noise.
Yeah,
Okay.
Google's is the best. I guess.
Yeah. So.
I found the CD on Mac is better.
Okay. Go ahead. Everybody, go ahead and applaud. Right? Just go applaud and let's see if as I talk and as I talk and there is applause. Right? Are there ways to for it? I think it's still working fine. Right? So we've had these demos where somebody's in a football stadium and there are people screaming their heads off and the speech is just still fine. I mean, it's not going to be as perfect as an empty room, but it's very close. It's getting there, right? So you shouldn't stop using it because you think of those conduct cases where you think it may not work, because even in those cases, we're getting there. And the more, now, again, all of these things go in as training, right? So over time, it'll just keep getting better.
But I cannot have my localized training set data over which I can.
Absolutely, you can, right? So all of these things, the speech API, every time you make a call to the speech API, you can pass in 500 words, right? Say these are the most likely words in this context, right? So for example, if you're building an application and you expect a person to say stop, right? You can say a very likely word is stop, right? And you can basically pass that in when you make the call. And because of that, the likelihood of stop, so even if they say stop, you'll still get it because it's learning to recognize that stop is a very likely word in this context. So you can pass in context-specific words to adapt the general API.
My question was, can I train my own data there?
Yes, you can train your own data, but how big is your data going to be?
So there was a problem we are trying to solve. We are figuring out with a Vision API. So back there in startup, we are trying to create a classifier.
Right.
So based on the
yeah. So that's not going to be Vision API. That's going to be ML, like Cloud ML. If you want to do image classification, and it's not something that's for example, if you're trying to detect is it a good screw or a bad screw, right? That's not going to be in our data set. But here's the way that typically that's done. What we do, so this is something that again you should watch out for. This whole idea is that you can basically build a model where the first 10 or 15 layers come from Google, and the last 3 layers are your own. Okay, the idea being that all images that you're using, the way to find edges, the way to find texture, the way to find text, all those are going to be the same. The important features are going to be there, but the actual classification, good screw versus bad screw, right? Or a bus that is, whatever it is that you want to classify, right? That part you do the training. The idea, then you can get away with training with maybe 10,000 examples. You don't have to basically have a training data set of 10 to 20 million. Right? Remember that all of these things that we're talking about, we're talking multi-million examples. You're not going to get this kind of accuracy with a few thousand. The way you get to a few thousand is we're building on top of Google, right? So use part of our model and then use yours. So not image recognition from scratch, but image recognition with the Google's inception model that gets you like maybe 80% of the inception model plus your own layers. But your layer is just a few layers. Does that make sense?
Makes sense. Is our mobile SDK is available for this speech API or just?
I'm not sure. I'm not sure. We can look that up.
And approximately.
It's a REST API, right? So any place where you can make a web call from, and that you have JSON. It's just a JSON thing that you're sending. Okay. So as long as you can send JSON and you can do that from mobile, so you can call it from mobile. The SDK part, I'm not sure about.
Because it's going to be in the form of like iTalk, and it's going to be an audio, I guess.
Right, an audio wave file that you keep uploading.
And that's what we got. So, what is the typical latency and data rate?
Okay, that's something that you pass in. It's part of the API itself. You can pass in the amount of data, the data rate, the speech data, etc. So those are all adaptable.
By data rate, I mean the network. What is the typical download?
Okay, it depends on where you are in the world. It depends on where you are.
Is speech API what we use with our
Yeah.
Google?
Yeah.
That's what we use, right?
That's what
then
you use.
We already are using that on mobile, so we can test out.
Yeah, so in terms of latency, it's not going to be identical. It's going to be similar to whatever your Android phone recognition takes.
Right. And it's all online. Right?
It's all online.
Speech to text is not offline at all.
No.
So with the Vision API, you send out an image and it sends you some metadata.
Correct.
Is there a query you can send and say, I'm just looking for this parameter?
Yeah. When you send it in, you basically say which of these 6 things you want, and it does only that part.
So in the photograph with the 3 people,
Yes.
if I want to know how many people in this image,
That isn't a supported thing. So you can only look for how many faces. Get me all the faces, and then you can count the number of faces. So that would be this layer that you build on top.
because there's no standard format in which I get back the data.
It is a standard format. It's a JSON format.
Yeah, but the metadata is not very standard. I need to learn how to interpret.
Speech API, do you recognize the number of speakers? This is speaker 1, speaker 2.
No, it's just speech. Yeah, we don't recognize voices. Yeah, or we don't externalize it. So in Android, for example, you can actually set up your phone to switch on when it hears your voice. Right? So you're doing voice recognition, but it's not externalized in the speech API, not yet.
In speech API, so if I tell like book Uber, would it categorize that keyword into a category of tabs and would it send us that as well?
No, that is a separate thing. So all speech API does is transcription. And then you have to basically add other things to it. Okay. That is called NLP. Okay, that's another API. It's not listed here, but the natural language processing API, it's also beta now. So you can use that and you can pass in the string book Uber and it'll come back with an entity called Uber. It'll give you a link to the Wikipedia entry for Uber. So you know exactly which Uber is being talked about.
So all these APIs, if I were to use in my, let's say, any of the startups, they want to use it for their applications. Is it on a paid basis?
Is it on a paid basis? Yes, it is on a paid basis. It's paid per call, essentially, with slabs. So that's what we looked at here, right? So the Cloud Vision API, the Cloud Speech API, the Translate API, the Natural Language API, which is what you were asking about, right? Identifying entities, identifying sentiment, all of these are meant for use by any developer, right? Because all that you're doing is that you're making a REST API call, passing in a JSON input and getting back a JSON. Okay. In between, we have, and then on this side, we have TensorFlow, which is basically an open source SDK where you write a whole bunch of machine learning code, right? And it gets executed on the best possible hardware, etc. And then in between, we have Cloud ML, Cloud Machine Learning, which is meant to be about auto scaling and making TensorFlow serverless. So just as you have Dataflow here, Cloud Dataflow, and you had Apache Beam, it's very similar. Okay, just like you have Spark and you have Dataproc, which makes running Spark jobs easier. It's the same kind of thing, right? So Cloud ML is this framework in which you can run machine learning jobs, run experimentation, do things in an auto-scaling way. But we also open source TensorFlow, so you're not locked in. So here, this is an example of TensorFlow itself. So this is what that looks like. So this is pretty complex Python code. Okay? So I'm basically creating a neural network, but this is the essence of it. Okay? I'm getting all my training data, and then I'm creating my neural network, which is my computation graph. And I'm basically saying, go ahead, and my cost is across entropy, minimize the cost. And at this point, all of my weights get created, and then I can get created. And then I basically feed in the data each time from my data set. So that's my input data, that's my labels data, and I feed it in batches. Right? And over time it trains, and at the end of it, I now have a set of weights, and all of those things get saved into my model file. And once I have my model file, I can then use it for predictions. Okay, so this is completely open source. The idea is that you can take this thing, and you can then run it inside Cloud ML, which will make it serverless, which will basically run it on very good hardware, because remember I said machine learning is really expensive. You don't want to run it on the regular CPUs, right? You definitely want to use at least GPUs, preferably GPUs, right? So to get that speed. But you can, again, you're not locked in. You can take a TensorFlow code, you can run it anywhere. Cool. So, summary then, right? What the cloud platform is about giving you auto-scaling serverless products. So they capture, transform, extract, analyze big data, and use it to build accurate machine learning models. The whole point of this thing is the auto-scaling serverless to basically deal with massive scale. And you can do this in real time, streaming data, on batch data. You can combine them. You can do your analysis in BigQuery. You can basically do your interactive stuff in Cloud Data Lab to do your Python notebooks. You can do Cloud ML to do machine learning. You can take your BigQuery and you can save it as a spreadsheet, and you can send that off to people. You can essentially take the BigQuery console, and this is something a lot of companies do. They would have these bunch of data scientists whose only job would be to create these little analysis things. And they finally said, we'll put our data in BigQuery. Anybody who wants to do your analysis, just go to the BigQuery console, type it, and do your analysis, right? And basically get out of that business of creating user interfaces if you have a kind of sophisticated. With that, I'll take questions.
Let's say I do want to use ML Cloud, let's say.
Right.
From your presentation, I got that in Dataflow, you can take any other machine learning library, like scikit-learn or any library,
Absolutely.
and use that and run my jobs somewhere.
Absolutely. Yeah, you can, right. Because again, Dataflow is Python, so you can do scikit directly, yes. And also you can use Dataflow to create your data set. And then once you create your data set, you can do some other, some other machine learning.
You can write Java code also.
Yeah, Dataflow can be Java as well. Java and Python.
So from a user perspective, of course, there's whole machine part where I think it's very clear that you simplify, don't have to worry about it. Now coming to especially the data model creation and usage of this, right? You'll find many of the startups are there, the guys, see reason because they have to create innovation comes there, right?
Correct.
And nobody wants to see that ultimately Google will do everything and there's no space left for anybody to innovate.
I don't think there's any danger of that.
Yeah, so that's the space has to be there. People have to innovate on top of that. Now, if I were to, for example, use Google capability to help get your data sets which are available to create model and take that model offline onto my computing thing and do that, is that a possibility?
Right, it's a possibility in certain dimensions, right? I would not want to compete against Google on language translation, right? That is very hard for you to win unless you are in a language that we are not currently in. Right? So those are the kinds of things that become very hard. If you're trying to solve those exact kinds of those problems that we're doing. But if you're trying to solve a problem for a manufacturing space, you're trying to solve a problem for a financial industry, right? You're trying to solve a problem in a domain, right? Domain-specific products around machine learning, it's completely open, right? None of the big majors are going to come in and try to create a,
See, IBM is doing for Watson. Healthcare they've taken away.
Right, but even it's not, the healthcare idea is like, I have serious doubts there. So about how well somebody without the domain knowledge is going to do at creating something that's very profound. Again, remember that I've been doing this for a long time, right? So people would always come in, like when I was in the weather thing, we constantly compete against these average people, right? They've done machine learning on all kinds of things, and they'll say, we'll come and build a weather machine learning stuff. We've done it all of these other places. But because we had the domain knowledge, we would always be 30 to 40% better than you. Always. So I have serious doubts about big majors being able to compete in the domain-specific space. They may have some product there, but I think that with domain knowledge, right, you can actually bring a lot to bear.
Feature engineering if you have good domain knowledge.
The domain knowledge is where you get the good feature engineering. Oftentimes, it also informs your choice of the data set, right? Because you tend to say, these are the corner cases, these are the things that if somebody just comes in and just randomly gathers data, they are not going to do as well as somebody who does it with forethought and knows what a human person has problems with and creates the data set from that perspective. So anything with domain knowledge would be definite places. Other cases would be niche things that are markets that are so small that the big guys won't come. But then that's obviously a very limited upside. So the thing I would really ask people to focus on are two things: domain knowledge and also machine learning enabled widgets. Like what I talked about with forms, for example. Imagine you had a widget that you can sell to somebody, like a software SDK. If they take this SDK, put it into your mobile app, and you will be able to do all of these things, right, in terms of speech, right? So you're basically building a higher level SDK. What we are doing is building this low level SDK around speech. You can build a higher level SDK that recognizes all medical terms, right? And then you basically go in and you sell it to a doctor for them to basically, every time they see a patient, they can type in, they can basically just speak their notes, and it recognizes that these are the words associated with this disease, right? And therefore, these are the words that come together, that does that clustering, so that the recognition, speech recognition, is much more than just a bunch of words. But the fact that the doctor has talked about fever, has talked about something that essentially makes some other words more likely, right? So then you can basically point at this is why we are going to be more accurate than the base speech that Google can do. But again, it comes down to using your domain knowledge to build a machine learning model.
So it comes down to how much pricing Google is offering for startups for this kind of area. Because that's a big area. So ultimately, if startup have to commercialize,
right,
this goes as a cost for a startup.
Right,
So,
absolutely.
So while the barrier becomes lower, now anybody can create, right?
Right.
So look at the way the trend will be, right? Look at 5 years down the line, all the fundamental building blocks, you don't work on it. It's a image recognition, voice recognition, you don't build them.
Yeah, it's
use
like
cases.
it's like long time ago when we were building GUIs, we basically place every button on the GUI. We don't do that anymore. It's exactly the same kind of stuff.
And still you get horrible websites today, right? You don't, because people don't understand user experience, right? So from engineering to user experience design, the transition is still we can do, right? So that way I see good. I mean, people will focus more on use cases. I mean, don't focus on fundamental engineering, focus on use cases. But there I think the full pricing aspect will be very critical, because ultimately that has to be taken into account as a cost for that.
You should talk to Anuja.
No, absolutely.
So we talked about the hybrid models, where we can use the layers of already learned model from Google
Correct.
and apply our own layers.
Right.
Is there an example of that?
We will be publishing that soon. Okay, that's but it'll be part of cloud.
Google has the DeepMind.
Correct. Yeah, we
Where
own
does that
DeepMind.
come in?
DeepMind is a user of TPUs, of TensorFlow, and all of these things. So DeepMind is one user, just like YouTube is a user. But they're a highly machine learning focused use cases and users. But that's what they are. They're a group within Google that uses machine learning.
It's a consumer of this.
It's a consumer of.
That's not going to be a product available.
No,
It's not
DeepMind
heading
is
towards
not.
that.
Yeah, DeepMind doesn't have one product. DeepMind has a bunch of things that they work with Google teams to help improve YouTube, to help improve speech, to help improve a variety of things. So they're a machine learning focused group that we call them ninjas, right? They basically get sent into a particular group to go and say, okay, there may be a group in Google that's been using machine learning and they've plateaued, and then these people come in and they say, okay, now how can you get the next one?
AlphaGo was an example of.
AlphaGo was built at DeepMind. It was not a this ninja thing.
Okay.
Yeah, but groups you don't hear about them externally, right? But the YouTube group or the ads group and all of those things, if you notice, like the ads are getting a lot better, but that's all because of machine learning. And those are all things that these groups are helping the other product groups do.
Let's say YouTube recommendations are not that great for individuals.
Right.
Whereas, let's say ad recommendation or other, so there are different teams, and some are focusing more and some.
And over time, everything will get there. Right? But yeah, there's a question of where each group within Google is in that journey towards machine learning, and also what they're focusing on. Ads are always the number one.
Yeah.
Right? No?
About to say that.
That's where we make our. Okay, here's I think the way we think about it. Our ideal situation for Google is that over a week you see only one ad, but that's the ad, right? So we want to reduce the number of ads you see, right? But make those ads that you see much more active. Right? That's where machine learning comes in. Okay, so it's good, and it's the whole idea. It's showing you hundreds of ads, only a few of which you click on, right? Or you use. It becomes the other way. Fewer, less is more. Can you share the roadmap for TensorFlow? I'm not sure I can. Okay, but I can talk about it very briefly. Okay, which is.
Anybody.
I'm sorry.
Will not tell anybody.
Will not take a picture of that.
So that's why I'll just talk about it, right? The roadmap for TensorFlow, right? So essentially, TensorFlow is going to continue getting enhanced, and so it's an open source thing. So TensorFlow is going to get TensorFlow serving, for example, which is basically this idea of you have a working model and then you have your production model, the thing that you can train all that. So TensorFlow is going to get continually enhanced in terms of, but it's not going to get much easier. So there's going to be a tf.learn, right? That's the easy use cases in TensorFlow for regression and so on. So that's one roadmap, right? The open source stuff is going to remain open source and it's going to get more features and more capabilities. Cloud ML is basically going to be about how do you build on top of Google, right? The first version of Cloud ML is you take a TensorFlow model and you run it within Cloud ML. Okay? But right now, the number of GPUs that we can offer to you are limited. Okay? They're going to come up soon. Right now, actually, with Cloud ML, it's in alpha, and the alpha customers are not even getting any GPUs. When we go beta, you will get GPUs associated with it. TPUs will still have to wait. Okay, so the roadmap is right now nothing, alpha. At the beta level, you'll get GPUs. And then once it goes GA, it will go GA with TPUs. Okay? And also means that that's just a hardware, right? The hardware the Cloud ML runs on. In terms of the software, that's some things I talked about. Right now, it's just machine learning from scratch. Cloud ML is just machine learning from scratch. But then we'll also build in machine learning with a hybrid model, right? With Google models as a base and build on top of Google. So that will come, and that's the second part. So you have to think in terms of 3 roadmaps here. Roadmap for TensorFlow. That's, again, anything that happens in TensorFlow automatically happens in Cloud ML, because Cloud ML is built on top of TensorFlow. So all of the ease of use and the extra capabilities will happen on the TensorFlow end. But the build on top of Google and the auto scaling stuff will happen in Cloud.
One more question I get asked is, what's the starting point for TensorFlow?
Okay. What is the starting point of TensorFlow? I would suggest that people avoid TensorFlow for now, right? And start with 2 things. Start with the ML APIs. Right? That's the first place to start for any machine learning thing. Right? You get so many things that you can do within any company with just the ML APIs. And then build up this momentum within any company, within any organization for why do we do machine learning, right? With the easy use cases. You can get started with machine learning with the API in an afternoon, right? One afternoon and you're in, right? And you basically, within like a month, you have 15 use cases. You've improved 15 products, right? And at that point, you basically go in and say, I want to build a custom model for this because it doesn't get solved. You will get more uptake. So first thing first, use ML APIs, right? That's natural language is so powerful, right? Given any text, we can tell you what people are in it, what places are in it, the sentiment of the text, what are they talking about. So there are so many use cases that can build around it without training anything. So that's where you start. The next place that you do is that then you build a TF.learn, right? The easy models, right? The easy models around regression, around classification, around those kinds of things. But you do them on a very case-by-case basis. You need them because it's your data can help. The way I think about this is Google data, your data, right? You have to make sure that you have enough data to make this part worthwhile. And this is all about making TensorFlow auto-scaled and easier to use and in an experimentation framework. So kind of making it less likely that you can make a mistake. You can still make a mistake when you're doing machine learning, but it helps kind of scaffold you a little bit, kind of forces you to divide up your data set, forces you to run hyperparameter studies, those kinds of things. Kind of gets you on the right way to do machine learning. So use Cloud ML to kind of be on the straight and narrow in terms of machine learning. But do this only after ML APIs. Do ML APIs first, and then make sure that you get enough money to collect enough data, and then you can do the other stuff.
Regarding TF-learn, it got merged into TensorFlow. Focus on that and adding more, let's say, generic APIs, so we can build more focuses on core TensorFlow.
Both. both. Again, it's not an either or case. So again, you need to make sure that there are two TF learns out there. There's a tf.learn that's in TensorFlow in the contrib, and there's a separate open source thing called tf.learn that's probably going to go away soon, right? So tf.learn is what I'm talking about, and right now it satisfies. It has a very Scikit-like interface. So you have an estimator, you have a regressor, you have a classifier, and the idea is to keep it that simple. Right? You want to keep the whole point of this is to keep it simple, and then the idea is that you drop down one level if you want to go a little more complex, and you can keep even within Tensor. So all of these are going to be layers in TensorFlow, where you start with the easiest layer and then you go down to the highest level. The way you think about TensorFlow, right, is how many of you use Java? A JVM, right? What's the purpose of a JVM? So you can execute code on different OSs, right? Portability. TensorFlow is exactly the same thing. TensorFlow is portable code. Portable between what? CPUs, GPUs, TPUs. Okay. So when you think about TensorFlow, think about JVM. Okay? That's a very low level. The lowest level of TensorFlow is that JVM-like thing. And then one layer higher is all the neural network stuff. Okay, so this is all the computation, not even the computation things. How to build a computation graph, how do you do multiplication of matrices, how do you do additions and all of those things. One layer above that is how do you build layers, convolutional layers, deep networking layers, neural network layers things. And then on top of that is tf.learn, right, which is basically classifiers, estimates, etc. The idea is you start at the topmost thing that works for you. And then you drop down one level when that topmost thing doesn't work. And then you go one level. If that doesn't work, you go next level. But it's all the same code base. It's like any JVM and Java language. You start with the highest layer of library, and if nothing works, you go all the way down to a J and I, right? That's essentially the same thing.
On this, you have APIs in Python and Java. If you have a model in R, is there a way to plug in?
Well, you can call, you can have R Python, right? So you can basically call Python models from R. That's basically what it is. We're not trying to build an R interface. I'm not saying never, but that's not an immediate plans. It's like we have these kind of code languages in Google. Python is one of them, Java is one of them, Go is one of them, R is not. So,
what about C++?
C++ is. Yeah, C++ is the code language. TensorFlow is in C++. So C++ is the code language. It's going to be supported. But something like C#, right? It's not a code language. It's going to be very low priority. So if one more language comes, it would probably go. That's about it. The core languages.
So what if somebody wants to contribute to TensorFlow?
Right. So there's a GitHub thing. You can basically go. There's lots of contributors. You can just go fork it, submit a patch. Absolutely open. It's truly open source.
In speech API, is there a way to get the numbers, the digits, other than displaying spelling of it?
Right.
Way to get the exact digit. We had a use case for that.
I see.
So that's a use case where someone can label.
But 3 would always be spelled 3, right? Can you not just do a string replace? But I think I see your point. If somebody says 3,000 or 3,000 or 1,300, right, or 1,300, you want them all to be the same thing.
I think the replacement is already. You can find libraries that.
You can, number replacements.
Maybe in future, that speech API will be an option. If there are digits being spoken, you actually write.
Right. So I'll take that back to the product team and ask them. If you can give me a card, I'll give you the answer. I'll ask the product team, and I'll email you the answer. Questions?
That's okay. So basically using the general NLP API.
Yes.
So in the past we tried out Stanford, but one was it was slow. Second, that what you get is too general that you can't use it in a domain specific. So a simple rule based would always be close to like similar thing to like having the domain experience.
Right.
You'll be able to do it.
Sure. So you'd have to try it out. So go ahead and try it out and use this. Let's see how well this does. We should be better than Stanford. Okay, but try it. I mean, it's basically based on a larger data set, so it should work with it. But it's one of those things that see if it works for a use case. If it doesn't work, just shoot me an email again. I can talk to the product managers, ask them for suggestions. One thing. The other thing is we can talk about like when sometimes there are capabilities that are in the pipeline. We can get you into an alpha that you can try things out.
Google ML API. Is it possible to summarize what let's say first I have a recording and I give it to speech and get the transcription.
Right.
Is there an API I can send the transcription, get a summarization of what they're talking about?
Yeah, that's a great thing. No, there is no abstracting thing, but I think that's a great use case.
You can do an LD on that and see how big model was.
Right. Yeah, you can do, but that's not really an abstract, right? It tells you the most important words, the topics that's being talked about. Yeah, you want to basically get an abstract. You want to get an automatic.
Tag them together.
I'm sorry?
You start tagging with the feature that you get out of it.
Yeah, so you can find the key topics that we do, and then you can find the key sentence that contains that, and so on. But that's hard. Yeah, I can easily see how we could do it naturally. So I think that's a great.
There's a Skype bot which does that. So if you just pass the HTML page, summarizes the whole thing.
Okay.
And that speaker thing will be great. Let's say I have a recording with two people talking.
Right.
In the transcription, if I can just get a speaker one said this line, speaker two said this line.
Yeah. Okay.
It is a very helpful use case. Sure. Some cases.
So who said what? Yeah. Okay. Neat. Yeah, I'll take that one definitely. That's a good point.
If I know there are two speakers, let's say I send the names. This speaker one, you can tag with this and this.
Yeah.
And then just in the transcript, if I get the names.
Right.
It becomes more.
It becomes much more usable.
Much more useful.
Yeah, definitely. I can see lots of use cases.
I get context of who is saying what.
Right.
So is the YouTube subtitles you get
Yeah.
transcript that you get, is it using the same?
Yeah. YouTube is. In fact, it's kind of funny because it was trained partly with YouTube, right? And then now that's normal machine learning, right? You have a small set of tagged samples. You basically train your model from it, and then you use it to basically predict on everything else. So that's what the YouTube thing is, the prediction problem. So some movies have closed captions. We could extract all of that and use it to do our training, and then turn around and just do it by default.
YouTube subtitles are not that great.
Right.
If we can add that real-time translation.
That can be.
Sorry.
It's fine. Yeah, again, all these things are coming up. They're just starting and moving along, right? So it's speech API used to be terrible like 3 years ago, and now it's
the best. Now it's just Watson and all, but this one's
really good, right? It's absolutely so. It's one of those things, right? It takes time. It happens. But thank you all for coming.
Thank you.
Thank you. I'll put up my email again. So feel free to shoot me an email, as I said.
Stop that.